if we do have an area where parts are above the x-axis and some parts are below the x-axis, we need to find these separately. So if we had a function that looks something like this, and we were asked to find the area bounded between this curve, y equals f of x, and the x-axis, well, that would be this area in here. But it wouldn't just be enough to work out the integral between this value and this value, because this area here, which we'll call area 1, it's going to give us a positive definite integral. And this value in here, which we'll call area 2, this will be negative. So the total integral, if we were to set limits here at, say, x equals a and x equals b, that total integral would actually be, well, going by the scale of this, it would be slightly negative, wouldn't it? Because this positive area would get overtaken by this slightly larger negative area. So really what would be better is if we knew all three values here, and we'll call them a, b and c, and we worked out area 1 first as the integral of the function between a and b, and then we worked out area 2 separately, which is between b and c. But because we now know that this will be a negative integral value, we would have to take the absolute value of that. Then we could say that the total area is simply area 1 plus area 2. So this is the approach that we are going to take for some examples that we'll do now. Number 1, find the area enclosed by the curve y equals x cubed, the x-axis, and the lines x equals minus 1 and x equals 3. So just like before, let's draw a sketch of y equals x cubed. Now keep in mind, when we're sketching, we don't always have to make our y-axis scale the same as our x-axis scale. So in reality, if we had a perfect scale, the cubic graph is much steeper, right? Like 1 cubed is 1, but then 2 cubed is 8, and 3 cubed is 27. So this looks a little bit flatter, but that's okay. We're just sketching. The main thing is we have a nice, consistent x-axis scale. Now you can also see here why we need the lines x equals minus 1 and x equals 3, because without them we haven't got an enclosed area. So let's add them in now, and voila, we have our area. Okay, so let's mark the first area on the left as area 1, and the area to the right of 0 we'll mark as area 2. And we'll also, just in advance, put a little note here telling ourselves that this integral will be negative and this integral will be positive. Alright, so let's start on integral 1. I'm going to call it integral 1 instead of area 1 because I'm not going to worry about the absolute value signs, but rather just work out the value of the integral. We'll do the absolute value later. So what are the limits for this area? Well, we're going from negative 1 to 0, and this is for x cubed. When we integrate x cubed, we get x to the 4 on 4. And so when we evaluate this, plugging in 0 is just going to give us 0, isn't it? So the first bit will be 0 minus, and then we're going to sub in negative 1. Now negative 1 to the power of 4, that gives us positive 1, and that's over 4. So we have an answer of negative 1/4 for this first integral. But remember, we want to take the absolute value of this to get the area, which means our area is 1/4 square units. Now area 2, we can just go straight to the definite integral because we know this will give us a positive result. And this is between 0 and 3. But it's for the exact same integral. So that's nice. We already know that that's x to the power of 4 on 4. And this time, when we sub in 3, we'll get a value, and when we sub in 0, that's just going to be 0. So we have 3 to the power of 4 on 4 minus 0. Tidying up, 3 to the power of 4, you could think of that as 9 squared, and that's 81. So we have 81 on 4 square units. Our total area is what we're after, however, so we want to add areas 1 and 2. So our total area A is the addition of area 1 and area 2, which is 1/4 plus 81 on 4. This gives us 82 over 4, and if we wanted to get a better idea of what this is, we could express it as a mixed number, which is 20.5 square units. And so that is our total area. Alright, let's do another example. Find the area enclosed by the curve y equals sine x and the x-axis in the domain minus pi to pi. So we should be familiar with what the curve y equals sine x looks like from 0 to 2 pi, because 0 to 2 pi is the conventional domain, so to speak. It's like one revolution around a circle in terms of an angle, 0 to 2 pi, or 0 to 360. So this is our sine graph for 0 to 2 pi, but we actually want to focus on minus pi to pi. And so here we go. So we are after this area. Now before we get into the calculations, what's something that you might notice? Well, because of the symmetry, or we could call it the rotational symmetry of this function, area 1, which we'll say is here, is actually going to be the same as area 2. But obviously, when we evaluate the integral, we will get a negative down here, whereas we'll get a positive up here. But this can allow us to actually take a little bit of a shortcut for this example. Whether we choose to work out area 1 or area 2 first, because they are equal, then the total area, which we would have said is area 1 plus area 2, we can just express as 2 lots of area 1 or 2 lots of area 2. And so we can actually halve our calculations in this case. While it doesn't actually matter which one we figure out, because we know that area 2 is going to give us, or the definite integral will give us a positive value, and it's also from 0 to pi, rather than negative pi to 0, this is probably the easier integral to calculate. Once we find its value, all we need to do is double it to find the total area. So let's go ahead and work out the value of area 2. Area 2 is definite integral between 0 and pi of our function sine of x. When we integrate sine of x, what do we get? Well, because the derivative of cos is minus sine, that means the integral of sine is minus cos. So we get minus cos of x. Evaluating minus cos of pi and then taking away minus cos of 0, what happens? Well, cos of pi is negative 1. So that means, so we've got negative, and then cos of pi is negative 1. Minus, what's cos of 0? Well, cos of 0 is 1. So in here we have negative 1. Alright, lots of negatives going on here, so let's be careful. But putting this all together, we get minus negative 1, which is 1, minus negative 1, so 1 plus 1, or 2 square units. Therefore, the total area, which is 2 lots of area 2, is going to be 2 lots of 2. And so our total area is 4 square units. Okay, so this example has led us to consider a few interesting things. So let's write some notes about those now. Let's first start with odd functions. Y equals sine x that we just saw, that's an example of an odd function. Now, graphically speaking, we can describe odd functions like this one here as having point symmetry about the origin. That's like rotational symmetry. I used that before. So I've made a copy, and as we rotate this, oh, voila. Not quite in the right spot, but as we've rotated it, look, it's identical. So that's one way to think of odd functions graphically. The other is to think about a double flip about the x and y axes. So if we took this part here on the positive side and we mirrored it or flipped it about the y axis, it would look like this. We'd trace out this path, and then if we flipped it again about the x-axis, then we would get this section here. So either rotational symmetry or a double mirror or a double flip about both axes gives us an odd function. Now, algebraically, this can be expressed as f of minus x being equal to minus f of x. Okay, and we've seen that before. And the cool thing about this is when we look at areas, this area here is exactly the same as this area here. And so if we were to find the integral between this value here, we'll call a, and this value here would be minus a. If we were to find the integral value, because the areas are identical, but one is positive and one is negative, they would cancel out and give us an integral value of 0, which is pretty neat. So for any odd function, y equals fx, we get this integral value. What about even functions? These are the types of functions where, graphically speaking, they only have one mirror, and that is the y-axis. So when you take what is on the right-hand side, where x is greater than 0, and you flip it, you get the exact same as all the minus x values. So algebraically, this is where f of x, so all the x values over here, is exactly the same as f of minus x. Okay, but what does that mean for our areas? Well, everything on the left is identical to the area on the right. And so if we're evaluating an integral between a and minus a again, then we can say this integral is equal to two lots of the integral from 0, so here in the middle, to a, or 0, or minus a to 0, but we'll just go with the positive side. And that was, we did use that idea of doubling in our previous example as well. So you can use that same sort of idea for odd functions too. So when you're completing questions yourself and you're sketching curves, keep an eye out for odd and even functions, and sometimes it can be worth actually testing in the first place if your function follows the odd rule or the even rule. Doing this little bit of extra work at the start could save you a bit of work later when you're evaluating your integrals. Alright, that completes our video. Great job.